This video is brought to you by mywayteaching.com.
In this part, let us study about thermal expansion. Okay. See, you may have observed sometimes the sealed bottles with metallic lids are so tightly screwed that one has to put the lid in hot water. For that, one has to put the lid in hot water for some time to open the lid. What happens if we put that lid in no, hot water? Why it opens when we put it in hot water? This would allow the metallic cover to expand, so thereby loosening it to unscrew easily. In case of liquids, you may have observed that the mercury in a thermometer rises when the thermometer is put in a slightly warm water. If we take out the thermometer from that warm water, the level of mercury falls again, isn't it? Similarly, in case of gases, a balloon partially inflated in a cooled room may expand to full size when placed in warm water. On the other hand, a fully inflated balloon, when immersed in cold water, would start shrinking due to contraction of that air inside that balloon. You try this. So take a balloon and you blow it and then try to immerse it in a cold water. Then you see that air inside that balloon will it will contract so that the balloon will shrink. So it is a common experience that most substances expand on heating and contract on cooling, isn't it? It's our very common experience that most of the substances, expand on heating and contract on cooling, isn't it? A change in temperature of a body causes change in its dimension. The increase in the dimensions of a body due to the increase in temperature is called as thermal expansion. Increase in the dimensions of a body due to the increase in its temperature is called as thermal expansion. Okay. See the expansion, if that expansion is in terms of length, that expansion in length is called as linear expansion. Okay. If that expansion is in terms of area, then that expansion in area is called as area expansion. And if that expansion is in terms of volume, then that expansion in volume is called as volume expansion. Okay. You can see in this figure, the first one is the linear expansion because it's expansion in length. Second one is area expansion, that is expansion in area. And the third one is volume expansion because it's expansion in volume. Okay. See, if the substance is in the form of a long rod, then for a small change in temperature, say delta T, the fractional change in length delta L by L, that is directly proportional to that delta T. If you consider a very small rod, if we increase the temperature slightly, that is delta T, then that fractional change in length delta L by L will be directly proportional to the temperature change. Okay, where alpha in 1 is known as the coefficient of linear expansion. And is characteristic of the material of the rod. You can see in this figure, it gives the typical average values of coefficient of linear expansion for some materials in the temperature range from 0 degrees Celsius to 100 degrees Celsius. Okay, for this table you compare the value of alpha 1 for glass and copper. This is 0.32 for glass and 1.7 for copper. And here we can see that copper expands about 5 times more than the glass for the same rise in temperature. So metals expand more and they have relatively high values of alpha 1. Similarly, if we consider the fractional change in volume, so if you consider the fractional change in volume, that is delta V by V of a substance for a temperature change of delta T, then we define the coefficient of volume expansion as alpha V. So that is given by the fractional change in volume 1 by the temperature change. So here alpha V is also characteristic of the substance, but it is not strictly a constant. It depends in general on temperature. You can see that in the graph. See here it is not constant in low temperatures. This alpha V becomes constant at high temperatures, isn't it? And this table, it gives the values of coefficient of volume expansion of some common substances in the temperature range, that is 0 to 100 degrees Celsius. Okay, you can compare this volume coefficients of different substances. You can see that even the thermal expansion of these substances is rather small, with materials like pyrex glass and invar, a special iron nickel alloy, having particularly low values of alpha V. And even from this table, we find that the value of alpha V for alcohol is more than mercury and expands more than mercury for the same rise in temperature. For alcohol, it is 110 into 10 raised to minus 5, isn't it? And for mercury, it is 18.2 into 10 raised to minus 5. So, here the value of alpha V for alcohol is more than that of more than mercury, and it expands more than mercury for the same rise in temperature. Okay. Other than these two, here they have given the values for aluminium, brass, iron, paraffin, glass, ordinary and even pyrex glass, hard rubber, invar, mercury, water, and alcohol. Okay. Water exhibits an anomalous behavior. What is that anomalous behavior of water? Let's see. What is that anomalous behavior of water? Which means it contracts on heating between 0 degrees Celsius and 4 degrees Celsius. So if you if you heat that water between these 0 degrees Celsius and 4 degrees Celsius, then it contracts. So it contracts on heating between 0 degrees Celsius and 4 degrees Celsius, and the volume of a given amount of water decreases as it is cooled from room temperature until its temperature reaches 4 degrees Celsius. As you can see in this particular graph, the volume of a given amount of water decreases as it is cooled from room temperature. So it decreases until it reaches 4 degrees Celsius, that volume, because it contracts. Again, it rises from 4 degrees Celsius. So below 4 degrees Celsius, the volume increases and therefore density decreases. So below that 4 degrees Celsius, you can see here, below 4 degrees Celsius, the volume increases. You can see up to 4 degrees Celsius, the volume is increasing, and hence the density, the value of density decreases. This means that water has a maximum density at 4 degrees Celsius. Okay, water has a maximum density at 4 degrees Celsius because at that point only it is having maximum density. You can see that in this figure. This is the point. This property has an important environmental effect also. So this is the anomalous behavior of water, which means between 0 to 4 degrees Celsius, whenever you heat that water, it contracts, and even the volume of the given in that 0 to degrees 4 degrees Celsius, this since that water contracts, the volume of a given amount of water decreases. Okay, as it is cooled from room temperature until it reaches 4 degrees Celsius. As you can see in this figure, then below 4 degrees Celsius, that volume it constantly it is increasing, as you can see in this particular figure, which means from this graph it is clear that the water it's having the maximum density at 4 degrees Celsius, and this property of water we call it as anomalous behavior, and this property has many environmental effects. What are these environmental effects? We'll see in the next part. Okay.